This is another example for double integration method in finding your slope and deflection in beams. So with this problem, we're given with a beam which has a pin connection or pin support at A, and then we have a roller support at B. So two loads are applied. You have 2 kip and a 4 kip load applied at 8 feet distances. So these are the dimensions given. So EI here is constant. So EI is constant. You have EI equals constant, or your flexural rigidity is constant, meaning your material is homogeneous. You have the same E or modulus of elasticity all throughout the length of your beam, and your beam is also a prismatic beam, wherein your moment of inertia does not change along the length of your beam. So you can also say that the cross-section does not change along the length of the beam. So that's a prismatic beam. And required here is to find the equation of the elastic curve, or essentially that's the equation for your displacement. Okay, the y is a function of your x. So in double integration method, first we will visualize the elastic curve. So for a pin connection or a pin support, you have a zero displacement but you have a slope, and same with the roller support, you have a zero displacement but you have a slope. So your elastic curve will somehow look like this. So this is now the deflection diagram, wherein you have to find the equation that represents this particular curve. So solution, we just have to find first the moment equation for the beam. So moment as a function of x. In finding this moment equation, we can cut this section, and then you'll have x from this point. So x will be from this point to that point. First, we'll find the reaction forces. So you'll have a reaction here at A, and then you have a reaction here at B. So RA y equals, that's if you sum up moments at B, you will have 4 times 8 plus you have 2 times 16. Diretso na natin, ha? Then you have minus 4. You have 60 divided by 8 times 3. You'll have 2.5 kips. Again, this comes from your, if you sum up moments at point B, you will have 4 times 8. 4 times 8 plus you have 2 times 16. Then you have 4 kip at the opposite direction, so you have 4, and then that's equal to RAY times your moment arm, which is 8 times 3, 24. So evaluate this, and then you divide 24, you will have 2.5 kips. And your RB is equal to 4 plus 2, that's 6, minus 2.5, that's 3.5 kips. The moment equation, again, you can make use of the left section of this section. So left portion of this particular section. So this section will look like this. So first we have a reaction which is 2.5. You will have a force of 2 kips, and then you have another force of 4. Then this is your section. And for your section, you'll have the shear which is directed downward. Then you have the moment which is directed counterclockwise. That's your moment as a function of your distance x. Okay, so this is a free diagram of the section. So your moment as a function of x is equal to, you have 2.5 times x, and then you will have, because the moment arm of 2.5 is x, and then you will have minus 2 times the moment arm, which is x minus 8. You have x minus 8. So this is x, no? Because you don't know the distance where you cut the section. So x minus 8, and then you also have another, the opposite direction, 4 times the moment arm, which is x minus 16. So these are the three forces that causes the moment at this particular section. Equate this with your EI, d squared y over dx squared equals your 2.5 x minus 2 times x minus 8 minus 4 times x minus 16. So integrate this. Our first integration will give us the slope or the dy over dx. So you have EI dy over dx equals integral of 2.5 is 2.5 divided by 2 x squared. So that's 1.25 x squared. The integral of this one is 2 over 2 x minus 8 squared. So that's x minus 8 squared. Then the integral of this is 4 divided by 2 squared. So that's minus 2 x minus 16 squared plus your constant C1. Okay? And then you integrate this again to give us the equation for y, or the displacement. EI times y, because the integral of this is 1.25 divided by 3. Divided by 3, that's 5 over 12. X cubed minus 1 divided by 3, that's 1/3. X minus 8 cubed. And then this one, you have 2 divided by 3 is cubed. 2 divided by 3, x minus 16 cubed. And then you have the C1, C1x, that's plus C1x, plus another constant C2. So this is now your equation for your EI times y. Now we have to find the value of these constants first. So you can establish the final equation for your displacement y. So you'll have boundary condition is at x equals 0. At x equals 0, you also have y equals 0. From the second equation, you can have c or C2 equals 0. So this is now eliminated. Next is we have to find the C1. There's another boundary condition at point B. That's if x equals 24, this distance again, your y is also 0, no? Because you don't have any displacement at point B. And then you can solve for C1 knowing that C2 is 0. So this becomes 0. And then you have 5 over 12. For example, you have to evaluate 24 cubed. And then you have minus 1/3. 24 minus 8, that's 16 cubed. And then you have minus 2/3. X minus 16, or 24 minus 16, that's another 8, that's 8. Plus C1 times 24, this is all equal to 0. Now, since your EI times y equals 0. So you just have to evaluate this. You'll have, by the way, they should be cubed. Okay, so that's 2/3 times 24 minus 16 is 8 cubed. So we'll have C1 equals, the unit is feet cubed. Because if you now have C1, you have C2, you can have the equation for y, which is equal to y equals 1 over EI. You just have to transfer EI to the other side. Then you will have 5 over 12, so we can erase this. You will have 5 over 12 x cubed minus 1/3 x minus 8 cubed minus 2 times x minus 16 cubed minus 8 cubed 2/3, that's 2/3. 1/3, 2/3 x minus 16 cubed plus or minus 169 x plus 0. So this is now your final equation for your displacement. So you can determine the value of your displacement at any value of x from 0 to 24.